Hello there, everyone. Welcome to another exciting edition of HL Chemistry Flipped Classroom. This is Mr. Los, and hey, how y'all doing out there? Right now, as I'm recording this, it's March 27th, 2020. It's a crazy time. The school is canceled. The coronavirus is in full swing. I don't know when you are watching this, maybe at some point in the future, or maybe you're watching it next week. But either way, what I want to do right now is talk to you a little bit about some graphical techniques that we didn't get to before break that have to do with the energetic stuff. And in the process of talking about these things, it is going to be a nice little review of energetics in general. So I think this is worth doing, and this is my Schoology page as it is currently. Actually, this is the energetics folder. So a couple of things that I would point out, and maybe in the future I have this set up a little bit differently, but these are a couple of data sets. These are files for a program called Loggerpro that I'm going to be talking about in a second, and those are things that might be useful, although not absolutely necessary. And then if we click here, a couple other things, the Loggerpro program itself. So that's what I'm going to be working with, and I think if it's at all possible, if you have a device that you could do this. In fact, I'm gonna blow this up here so we can get serious. I would really highly recommend that you download this software and use it because it's free and it's a great piece of graphing software. You could use it your whole academic career. It is much better than using Excel or anything like that to do scientific graphs. So, if you have the device, I would take this opportunity to download this program and use it. I think it's a great program and something that's well worth investing your time in learning how to do. So there is a link here. You have to download this from a specific link, and again, in future years, I may be making this available some other way, but for this year in 2020, you want to click this link. Also, and so you can download that program and do it before. I would stop the video right now and do that if you haven't done that already. And then also here is, and again, maybe in future years you have a paper copy of this or whatever, but if you could print this, it would be awesome. If you don't have a printer, I get it. It will be fine. We'll work around that. We'll figure it out. Okay. So let's get started. What I'm going to do is magically open the Loggerpro program here, and what I'm going to do is I'm going to open those two files that I just mentioned to you that you'd want to pull down off of Schoology and download locally to your computer. I'm going to open those up, or I'm going to open the first one up. So the first one goes with the first problem on that little worksheet, and the second one goes with the second one on that worksheet. And let me just find it here. One, energetics. And so I'm going to open up data set 1. That's the first one that we're going to take a look at. And in that worksheet, so basically we have an experiment where people are trying to find the delta H of a reaction. And so this program is a program that can generate scientific graphs, but it's also part of a set of hardware that can be used to collect data over time. Like this one is a thing that's collecting temperatures over time. So it can automatically, it's called a data logger. It can automatically log temperature over time. So this one has logged some temperatures over time for the reaction 1. So reaction 1 is here. We've got 100 cubic 50 centimeters of 0.5 molar copper 2 chloride in a styrofoam cup calorimeter. So we got the temperature probe in there. We add 4 grams of zinc to it, and we've monitored temperatures for 60 seconds. So what you're seeing is the temperature change that have happened over that time period. And basically what we're trying to do is calculate the delta H of that reaction right up there. Of course, that question mark should be an arrow. So we're going to try to find the delta H of that reaction. And we've done problems like this. This is going to be a nice little review, but we're going to add a little tweak. We're going to do something graphically that can help with one of the biggest problems, maybe the biggest problem with energetic experiments, which is heat loss. So if we go back to our data here, so we see we initiated the reaction somewhere around here. The temperature starts going up and it climbs, but of course the calorimeter is not a perfect calorimeter, so it's losing heat energy. We can see that the temperature is decreasing back towards room temperature. Now, a absolutely perfect calorimeter that lost no heat energy nor gained any heat energy would increase, and then it would stay the same forever. But this one doesn't. So we're losing heat energy here. So watch, there's something that I'm going to do. And you can do so much stuff with this software, but this is just kind of the tip of the iceberg. I'm going to try to find about where the temperatures start decreasing. And if you were able to download the program, probably kind of like in some degree doing this with me, I realize you're kind of watching the video and all that, but a little bit of back and forth would probably be good. I'm going to try to find about where the temperatures start decreasing. So there-ish right there. And Loggerpro can put all kind of curve fits. I know the way, I don't know, it's the resolution or something, these buttons are tiny up there, but this button is a linear fit. So if I press this button, Loggerpro is going to try to apply basically a straight best fit line through that data. So I'm going to click that, and there it is, and I'm going to move that, and it gives me a nice little equation for the line and all that good stuff. I can't remember to what degree we've talked about these values and what they mean, but basically, the closer this one is to 1, the more convincingly linear the data is, or the more linear the data is. So that's not bad, and this one being closer to 0 is more convincing. So this data is decently linear, is what that says. So I have a line here, and another thing I can do is if I go up to Analyze here and I click both Examine and Interpolate, you want to click both of those. What you'll see is right where my cursor is, you see how there's a little line? I can trace along that little line, and it's giving me times and temperatures for every one of these points. So I can kind of trace along my line and use this line to find times and temperatures, I guess, along X and Y values along this line here. So normally what we would do in this kind of experiment is we would find our delta T just normally. I would say, okay, there's my TI, find maybe the highest temperature I got to. Oh, that's the highest temperature I got to right there, and subtract them and get our delta T. But there's heat loss, right? In this case, since this is an exothermic reaction, that temperature should have climbed to some higher value. If there was no heat energy lost, it would have climbed to a higher value. And we're going to use this best fit line to try to guess the temperature that it would have climbed to had there been no heat loss. And this is a bit tricky to be sure, but I want to make it absolutely clear to you that IB expects that you know how to use this graphical technique. I've seen it show up on exams where they show a graph like this and they don't tell you to do what I'm about to do, but they expect you to do it. So unfortunately, this is something that we need to be familiar with. So here's the logic, right? So the temperature we seem to be losing heat energy at a fairly linear rate, or at least the temperature is decreasing at a fairly linear rate. So we're going to make a couple of assumptions. That linear rate of heat loss has been happening through the whole experiment. And we're also going to pretend that this reaction happens like instantaneously. And so I'm going to, this line, if you think about it, see my little circular, I almost pointed to it, but you can't see what I'm pointing to. This little circular line, you see that I'm moving up and down right now and is tracing along the best fit line. What this could be used to do is extrapolate forward and backward in time. And by the way, another thing that's cool about this program here, like things like rescaling axes and all of that are just as easy as this. Like I can drag these axes up and down if I want to rescale things, see things in more or less detail and all that. So I might want to do that. There's time 0 is right here. Time is on the x-axis. So anyway, I can go backwards and forwards in time along this axis. What I want to do is I don't want to go all the way back to like before, time -1 or whatever. That wouldn't make sense. I want to go right to when I actually initiated the experiment. And if you look at the write-up that we'll go back to in a second, it does say they waited a few seconds before they actually put the zinc in. So the reaction appears to have started about right here, because then I see this big jump. So notice if I just try to put the cursor right here, if you notice right up above the little box, the square box, it says a time and a temperature. It is telling me the X and Y values right here where my little cross-shaped cursor is right now. And so at that point on the line, we have a time of just over 3 seconds and a temperature of 36.48. So what we're assuming is basically the heat energy has been lost at a linear rate. We're using this best fit line to kind of go back in time to when the reaction started as if there had been no heat loss. So what this is telling me, or I'm using this graphical technique to predict that my final temperature was actually going to be 36.487 if there had been no heat loss. And so we're using this graphical technique as a way to help mitigate or eliminate the effects of heat loss, which are a significant problem in all energetic experiments. So jot this information down if you have your if you have your worksheet in front of you, or even just on a piece of scratch paper or whatever you want to do this on. Let's jot down our final temperature here. We're going to call our TF 36.487. Now, probably if we think about things like measurement uncertainty, the uncertainty on the temperature probe that would have been used to do this would be 0.1. So really, we should probably only record this to the 10th spot. So let's call it, we're going to call it 36.5. And then I'm going to go back to the document here and we'll finish working this problem. But basically, again, instead of using the highest temperature that it actually got to, I'm using this value to predict the temperature it would have gotten to if there had been no heat loss. 36.5 is, I think, what I said we're going with. Okay, so back to our problem here, and this will be a nice review for solving these kind of experimental delta H problems in general. Okay, this is going to be weird. It'll be a nice review of that kind of thing. I'm going to take this off so you're not looking at the ceiling. All right, so we got 150 cubic centimeters of the 0.5 mole per cubic decimeter copper chloride. So the first thing we're going to want to do here is use good old Q equals MC delta T. As I've said many times before, the big issue here is what to put in for mass. So we need to think about where the thermometer is. The thermometer is in this styrofoam cup. It's got this solution in it, which has mass. And then we're also adding the 4 grams of zinc. I'm going to make that assumption that that solution has the same density and specific heat as water. So let's call that 154 grams. And the specific heat of water is 4.18. That is joule per gram degree Celsius. And then the delta T. So the initial temperature, I don't think I pointed this out, but if you go back and look or back up, it was about 20.1 degrees Celsius was where it started. And then our extrapolated temperature, I think we said, was 36.5. And again, I'm rounding that to 1 digit past the decimal because of the uncertainty of the measuring device that we used. So we're looking at a delta T there of about 16.4 degrees Celsius. So we'll pop that in there. And then just make this calculation, 154 times 4.18 times 16.4. And we want to think a little bit about units here. So I get 10,557. That's plenty of significant figures. Grams cancel here, degrees Celsius cancel here. So far we're in need of joules, but we need to get this thing to kilojoules per mole. It doesn't say that explicitly, but that's the unit we want to calculate delta H's in of reactions, plus also we have this expected value here, so we'd want to be able to compare it to that. So first of all, change it to kilojoules. That's easy enough. That'll also can solve our significant figure problem. Let's call it 10.6. Now, another issue here, and this is a confusing point that comes up often, is what about the sign? So remember, the thermometer really is measuring the temperature of the water. We need the temperature of, and so the water is part of the surroundings. So from the water's point of view, it gained 10.6 kilojoules of energy, but the system, this reaction, lost that energy. So this is an exothermic process. And pretty much always, in every situation I can think of anyway, when you use this type of situation, these type of calorimetry, you're going to have to flip the sign. Still, though, our unit is only kilojoules. So there's a little bit more that we need to think about here. So we have our chemical reaction. I'm just going to rewrite it, or I'm going to rewrite the reactants anyway. Because unfortunately, we have to think about limiting reagents here. It says we have 4 grams of zinc. Now, zinc's a solid. And then it says we have 150 cubic centimeters of 0.5 0.50 mole per cubic decimeter copper chloride. So what I should do is change both of these to moles. And that way I can make the comparison. So 4 grams divided by zinc's molar mass is about 63.55. 63.40 rather. 65.40, call it. There we go. And so we can find moles that way. Just figure this out here. 4 grams divided by 65.40. That is about 0.0612 to 3 significant figures, call it, moles of zinc. To find my moles here, let's change this to cubic decimeters, 150 cubic decimeters, and use our concentration as a conversion factor. And every 1 cubic decimeter, there is 0.50 moles. So that's 0.075 moles. Now, we've talked about different ways to find the limiting reagent, but you could simply divide by the coefficient, and whatever one's smaller is going to be limiting. Of course, since it's a 1-to-1 ratio, this is obviously going to be the same number, so zinc is limiting. Whatever one we have less moles of, fewer moles of, is going to be limiting, so it's going to be zinc. And this is all to say that in this next step, I need to be using the value of the limiting reagent. It works the same as if we were doing any kind of stoichiometry, whether you're talking about energy production or production of a product. You need to use the limiting reagent. So the mole ratios are 1-to-1, so you don't need to worry about any of that kind of stuff. You could do a proportion. I mean, really, we're just going to be dividing 10.6 by 0.062. But if you want to set a proportion, that would always work. Where when we did the experiment, we got negative 10.6 kilojoules from 0.612 moles. Therefore, we would get x kilojoules from 1 mole of zinc. So we're kind of proportioning it upwards to the actual proportions in the balanced equation. And so we get 10.6 divided by 0.0612. And we get 173, negative 173 kilojoules per mole. So we're still pretty significantly far off from this expected value that we have up here of negative 219. We're less off than we would have been if we had not used this technique to mitigate some of the heat loss. So, you know, there could be a variety of other experimental errors happening here. To be honest, I kind of fudged those numbers in that thing that we saw there. You know, IB claims that this technique works. I've found that actually, if you really do it, it often overestimates, and you actually get values that are too large often when you do this. But you know, supposedly according to IB, this is a helpful technique that actually works. So that's what we're going to go with. Okay, so that is the first problem. That's all we really, I know it was a lot, but that was all we needed to do really for that first one, is just come up with the experimentally determined delta H of the reaction. We came up with negative 173. So let's take a look at the second one. So my suggestion would be if you were able to download Loggerpro and get that working, go ahead and open the second data set and just kind of, you know, play around with it a little bit and see if you can you know, generate the line, the best fit line that I was showing you before. So this was the first data set. Here's the second data set. No, we're not going to save our changes to that. So yeah, here we have another one, and you can play around with the scaling by, I'm just clicking and dragging right on these axes here. So you can do that. So remember, you can highlight any portion of this, but we want to highlight the part where the heat loss is happening. And then here is where the different curve fit options are. So if you are doing this and you do have Loggerpro, you might want to pause it and just see if you can figure this out, like figure out how to get it to work from that aspect. But if you don't have it or got stuck or just want to see what's going on here, we can see the reaction is initiated right here. The heat loss seems to happen somewhere in this area. So I highlight it, and I want to do a linear fit, which is this tiny little button right here. Boom. That's the line. You can move these things around if you want, once you have those. Here we have an even better correlation, even more convincingly linear. And then the thing is to make sure that under Analyze, both Examine and Interpolate are checked. That's the best thing to do. And then we can look at time and temperatures for various points in time. And we're going to assume this heat loss is linear. Whoops. And we're going to go back in time to right about when the reaction got initiated, which is roughly right about there. And so the temperature I'm seeing is 56.994. Again, we should probably be only 1 digit past this, but let's call it even 57, just to make our lives easier. So we're going to use that for our maximum temperature instead of whatever maximum temperature we actually got to here, which was like 52.3. We're going to use that 57 and call it good there. So this video is getting on the long side, so what I want to do is have you guys take a shot at solving this problem. You know, the challenging part, or maybe the most challenging part, or the new part, is getting to that idea where we're going to use 57 as Tmax. But knowing that, it's going to proceed pretty similar to the previous one. We do have some coefficients here to worry about, so we need to think about that. But I'd like you to try to get that, and then I'm going to pop back on and just show you mine worked out and just very quickly show you the answer. For part 2 here, you would have to use a table of heats of formation, a full table of heats of formation, not the one that IB gives you, but the full one that I gave you and like the extra thing. And it's a little bit confusing, but you would have to do the products minus reactants heat of formation thing, and so I will pop back on and walk through that as quickly as possible as well. So go ahead and pause the video now and give that a shot. Okay, and we're back. One quick note here, what to use for TI for the initial temperature. Some of you, if you tried it, may have used some value in here. To me, this probably looks like the best one. If you worked with one of these, that's fine. It's more about the process, but it looks like the reaction started, you know, the thermometer kind of came up to the temperature, the initial temperature of the solution, and then they started the reaction somewhere in there. So I used 20.1. But let's go ahead and take a look at this. So again, just to run through this very quickly here, using the total mass of the solution times 4.18 times the delta T, that's when we use 20.1, that's where we got the delta T. Flip the sign, change to kilojoules. And then the other stuff that we need to think about is limiting reactants. So what I did was I converted both of these to moles and converted that to moles. This time there is a 2:3 ratio, so limiting reagent trick, whatever number is smaller when I do that is limiting, which this time turns out to be the CuCl2. And basically the reason I do that is that's going to determine the choice that I make over here in regards to how to proportion this upwards. So in the case of this one, since this is limiting, when we did our experiment, we got this many kilojoules from this many moles of CuCl2. And when I did this the last time, technically what we're solving for here is the unit of kilojoules per mole, and I proportion it up to a 3. If aluminum hypothetically had been the limiting reagent, I would have put aluminum's moles here, the 0.111, and then I would have put it at 2. Because we're basically portioning up our energy loss so that it matches the coefficients in the balanced equation. That's what you need to do to find the delta H of a reaction. So that's that one. And again, that's quick. If you have questions, you know, if it's a normal class, you can ask me in class. In this distance learning situation, you can message me. You can. There's a discussion board for energetics questions. You can ask it there, or what have you. As far as the expected value, now, I don't really want to worry about this too much. It's not so much how to do the problem, but where to find the information, and that part's a little tricky, and it's just beyond the scope of what we need to do. But what you would want to do would be heat of formation of products minus heat of formation of reactants, and the elements by definition have 0 heat of formation, so we can ignore both the aluminum and this. So what we need is the heat of formation of aqueous aluminum chloride and aqueous copper 2 chloride. Those are U's, they look like A's. And so I do products minus reactants, so I do this one minus this one, ignoring both the elements, and you're going to get something right about like this. And I'm not even sure I had the right information, so Again, let's not worry about this a ton, except for the fact that we should remember that we can do this from heat to formation and do products minus reactants. In this specific context, in answering the information, getting the information you needed to solve this specific problem is a little tricky, and I don't want to worry about it. But thanks for watching, guys. I'm sorry this one got a little bit on the long side, and I hope you're doing as best as possible out there. If this is 2020, you're isolating, I hope things are going as well as possible. And I hope to see you in person again soon. Thank you.